Hello everyone, myself Kirti. It is an audio lecture for visually impaired students on the topic non-aqueous solvent from inorganic chemistry. So let's start it. Non-aqueous solvents. Most of the chemical reactions are carried out in solutions and the behavior of substances also depend upon the nature of the solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, ease of purification together with its favorable physical and chemical properties such as long liquid range, that is 0 to 100 degrees Celsius, high dielectric constant, specific heat, heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a long variety of substances. In fact, the excellent property of water have hindered the development of non-aqueous solvents. The solvents other than water which are used for carrying out chemical reactions are known as non-aqueous solvents. Attempts have been made to find some other substances which could behave as good solvent like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now, there are many other solvents available, for example, liquid ammonia, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important features of non-aqueous solvents such as ammonia and sulfur dioxide. Physical properties of solvent and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reaction and separate the product more conveniently. Some of the important physical property of the solvents are discussed below. First is melting point and boiling point, that is liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reactions in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which the solvent is useful. The melting and boiling point for some common solvents are given in the table. This is the table for melting and boiling points of some common solvents like water, ammonia, hydrogen fluoride, sulfur dioxide, acetate, etc. It is clear from the above table that water has excellent liquid range between 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as a solvent at ordinary temperature, while ammonia and sulfur dioxide can act as solvent only at low temperatures. Second property is heat of fusion and heat of vaporization. The values of heat of fusion and heat of vaporization help to know the nature and strength of forces which hold the molecules of the solvent together in the solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger are the intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitude of molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of the intermolecular forces, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Toronto constant, that is, del H of vaporization upon Tb is equal to Toronto constant. Here Tb is the boiling point. For normal liquids, if molar heat of vaporization are expressed in calories and boiling point in absolute scale, that is 0 Kelvin, then the Toronto constant has the value 21.5. If del H of vaporization are in joules, Toronto constant is about 90 for normal liquids. Such liquid exist as independent molecule without any bond between them. A higher value of Toronto constant indicate associated molecules. For example, common solvent like water, ammonia, hydrogen fluoride have Toronto constant value greater than 21.5 and are therefore associated liquids. The molecules of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositely charged end of the molecule come near to each other. The molar heat of fusion and vaporization of some solvent are given in table 2. Here is the table for molar heat of fusion and vaporization of some solvent like water, ammonia, sulfur dioxide, hydrogen fluoride, etc. Third property is dielectric constant. This property is a measure of the polar nature of the solvent and help to estimate the solubility of polar or non-polar substances in the solvent. According to Coulombic law, the force of attraction between two charged ions is given by F is equal to Q positive into Q negative divided by epsilon naught R square, where Q positive and Q negative are the charges of the cation and anion respectively. R is the distance between them. Epsilon naught is a constant called dielectric constant of the solvent. If dielectric constant is large, the force will be small. As a result, only a small amount of energy will be required to separate the ions, and hence it will be easy to dissolve an ionic substance. Thus, in solvent of high dielectric constant, the ionic substances will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compounds will decrease. The dielectric constant of some common ions are given in the table 3.3. Here is the table for dielectric constant of some common solvent like water, ammonia, SO3, acetate, hydrogen fluoride, hydrogen cyanide, DMF and sulfuric acid. It is clear that solvent like hydrogen fluoride and water are good solvent for ionic and polar compound because of their high dielectric constant values. The value of dielectric constant for hydrogen fluoride is 83.6 at 0 degrees Celsius and for water it is 81.7 at 18 degrees Celsius. For example, carbonate, sulfate and phosphate are practically insoluble in liquid ammonia or liquid sulfur dioxide. Fourth property is dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvent having high dipole moment have greater tendency to dissolve the polar or ionic substances. This is because of the fact that the greater polarity result in stronger bond between the solvent and the solute molecules and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecule and help in dissolving the solvent. Fifth property is viscosity. It is a measure of the fluidity of the solvent. Solvent like water, ethyl alcohol and carbon tetrachloride have low viscosities and are highly fluid and flow rapidly under ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosities and flow at much lower rates at ordinary condition. In solvent of low viscosities, The operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increase in the viscosity of a liquid, increase the difficulty of such operations. Next topic is types of solvent. There are four types of solvent. First is protonic and non-protonic solvent. Second, acidic, basic and amphiprotic solvents. Third is ionizing and non-ionizing solvents. And fourth is coordinating and non-coordinating solvent. Firstly, we will study about protonic and non-protonic solvent. The solvent from which protons means H positive ions can be derived are called protonic solvent. Therefore, protonic solvent contain ionizable hydrogen. Common examples of protonic solvents are water, hydrogen fluoride, H2SO4 and HCN. The solvents from which protons cannot be ordinarily derived are called non-protonic solvent. These are called aprotic solvents. In other words, these solvents do not contain ionizable liquids like SO2, N2O4, C6H6, CHCl3, CCl4. Second is acidic, basic or amphiprotic solvent. This classification is based upon the acidic or basic behavior of solvent. The solvent which have a strong tendency to donate proton are acidic in nature and are called acidic solvent or protogenic solvent. For example, H2SO4, liquid hydrogen fluoride, acetic acid, etc. Solvent which have strong tendency to accept proton and are basic in nature are called basic or protophilic solvents. For example, liquid ammonia, pyridine, hydrazine, ethylene diamine, etc. The solvent which neither have a strong tendency to gain nor a strong tendency to lose protons are called amphiprotic or amphoteric solvents. In other words, they neither behave as a strong acidic nor basic but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Third is ionizing and non-ionizing solvent. The solvent which are capable of undergoing self-ionization are called ionizing solvents. Some common examples are water, ammonia, hydrogen fluoride, sulfur dioxide, N2O4, ClF3, BrF3, POCl3, etc. These ionize at their own. These solvents are generally polar or ionic in nature. On the other hand, the solvent which do not ionize at all are non-ionizing solvent. Some common examples are benzene, carbon tetrachloride, hydrocarbons, etc. These are non-polar or non-ionic in nature. Fourth is coordinating and non-coordinating solvent. The solvent which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. For example, ammonia, sulfur dioxide, dimethyl sulfur dioxide, acetonitrile, dimethylformide, nitromethane, etc. On the other hand, the solvent which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvent. For example, CCl4, saturated hydrocarbons, etc. These are not of much interest to inorganic chemists. Next topic is types of reaction in non-aqueous solvent. The following types of reactions commonly occur in non-aqueous solvents. First is metathetical or precipitation reactions. The reactions in which precipitation occurs on mixing two solutions are called methetical or precipitation reactions. These type of reactions can be predicted if the values of the solubility product of the compound formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride. leaving barium nitrate in the solution. On the other hand, in liquid ammonia, a precipitation of silver chloride combines with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. Second reaction is salt formation. The reactions between appropriate acidic and basic substance to form salt are called salt formation reactions. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, urate cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water and uride will take a proton from water to form hydroxide ion. However, this salt can be easily formed in solution, that is liquid ammonia solution, by the reaction of urea with strong base sodamide. Third reaction is acid base reaction or neutralization reactions. The acid base reaction in non aqueous solvents can be explained on the basis of solvent system concept. As already learnt, according to solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvent gives the cation characteristic of the solvent. Similarly, a base is a substance that gives the anionic characteristic of the solvent. The acid-base behavior of a substance depends upon the acid-base nature of the solvent, the character of the solute, and the solute-solvent interaction. In the case of protonic solvent, cation is the solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, ammonium ion act as a acid in amide ions act as bases. In non-protonic solvent such as benzene, carbon tetrachloride, Lewis acid base type of reactions can occur because of non-ionization of the solvent. The acid-base behavior of a solute in a solvent depend upon the acidity or basicity of the solvent. For example, acidic acid behave as strong acid in ammonia, weak acid in water, but a base in sulfuric acid. Fourth type of reaction is solvolytic reactions or solvolysis. The reactions in which the solvent molecule react with the solute in such a way that the solvent molecule split up into two parts, on or both of which get attached to the solute molecule solvent, are called solvolytic reactions. Since these reactions occur through self-ionization of the solvent, the concentration of either the cation or the anion is changed. Next is solvation reactions. The reactions in which the molecule of the solvent get attached to a solute species, that is cation, anion or molecule, are called solvation reactions. The species formed is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alkylation, etc. and the resulting solvents are called hydrates, ammoniates, alkylates, etc. Solvation of a cation occurs through ion dipole interaction between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecule donate a pair of electrons to the cation. On the other hand, solvation of anion occurs through ion dipole interaction between the negative ion and the positive end of the solvent dipole, or through hydrogen bonding in case of solvent such as water, ammonia or hydrogen fluoride. Next topic is liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvent. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of the physical property resemble those of water. The property, that is the physical property of ammonia and water, are given in the table. Properties like freezing point, boiling point, density, dielectric constant, viscosity, specific conductance, dipole moment, heat of fusion, heat of vaporization, etc. Comparison of properties of liquid ammonia and water. First, liquid range. The melting and boiling point of liquid ammonia are lower than those of water. In liquid ammonia, the liquid range is from -77 to -33 degrees Celsius, and therefore it presents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. Second is hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element, nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen. Third is dielectric constant. The dielectric constant of ammonia is 22 at -33.5 degrees Celsius, which is lower as compared to water, which is 78.5 at 25 degrees Celsius, suggesting its lesser tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic substances. Fourth comparative property of ammonia and water is self-ionization. Both ammonia and water show comparable self-ionization properties. Now, ammonia is considered as a better solvent than water because of the following properties. First is liquid ammonia is a very poor conductor of electricity. Second, the specific heat of ammonia is more than that of water. Third, liquid ammonia is less viscous than water. Most salt, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionizing power of ammonia, but due to low viscosity, which greatly increases the mobility of the ions. Fourth, liquid ammonia has high critical temperature and pressure. Fifth, it is less associated than water and therefore is a better solvent for organic compounds. Sixth, liquid ammonia forms strong reducing metal ammonia solution with alkali metals. Therefore, it is an excellent solvent for many reduction reactions. Next topic is reactions in liquid ammonia. As mentioned earlier, ammonia has water-like property as a solvent. It is therefore expected that the reactions which take place in aqueous solution can also occur in ammonia solutions. Some of the important chemical reactions occurring in liquid ammonia are given below. First is acid-base reaction. The acid-base reaction in liquid ammonia can be easily understood by comparing the reaction in water. According to solvent system concept of acid and base, the substance producing hydronium ion in water act as acid while those producing hydroxide ions act as base. Liquid ammonia ionizes as NH4 positive and NH2 negative ion. Therefore, the substance producing ammonium ions in liquid ammonia behave as acid, while those producing amide ions behave as base. Next is proteolysis. Certain compounds like urea, acetamide, sulfamide, etc., which are incapable of donating protons to water, can readily donate protons to NH3 in liquid ammonia. These reactions are called proteolysis reactions. Hence, these reactions act as acid in liquid ammonia. These are some reactions of ammonia given here. Next is acid-base neutralization. In aqueous solution, the process of neutralization of a strong acid and a strong base involves the combination of hydronium ion from acid and hydroxide ion from base to form practically unionized water. For example, the neutralization of hydrochloric acid and sodium hydroxide may be expressed as HCl plus NaOH gives NaCl plus H2O. In a similar way, the neutralization of an acid and base in liquid ammonia involves the combination of ammonium ion from acid and amide ion from base. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both in acid and base are called amphoteric substances. As an acid, it gives ammonium ion and base gives amide ion in liquid ammonia. These are termed as amino acid and amino base. Reactions of amino acids. Amino acid is a substance that furnishes ammonium ion in liquid ammonia. Ammonium halides, nitrate or thiocyanate are very soluble in liquid ammonia, giving ammonium ions, and their concentrated solutions act as amino acids. We know that acid give hydrogen with metal in aqueous solution. In a similar way, the amino acids react with alkali and other metal to give hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolves many metal oxide similar to their behavior in aqueous acids. Solution of ammonium halides in liquid ammonia may be used as acid in the preparation of silane and arsine. Second is reactions of ammono bases. Ammono base is a substance which in liquid ammonia solution gives amide ion. The commonest base is potassium amide, which is much more soluble than lithium and sodium amide. Metal salt react with ammono base to give amide, imides and nitrides which get precipitated in liquid ammonia. Second reaction is precipitation reaction. The first reaction of liquid ammonia is acid base reaction, and now the second reaction is precipitation reaction. Precipitation reaction involve double decomposition because of the difference in the solubilities of various substances in water and in liquid ammonia. A large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. For example, silver chloride is precipitated in aqueous solution. Similarly, a white precipitate of barium chloride is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. Lithium chloride may be precipitated by the reaction of ammonia chloride and lithium nitrate in liquid ammonia. Second is iodides and bromides get precipitated when solution of various nitrates and ammonium halides in liquid ammonia are mixed together. Third is many metal sulfides can be precipitated in liquid ammonia by ammonium sulfate from the nitrate solution of the metal. Third reaction of liquid ammonia is ammonolysis. The solvolysis reaction in liquid ammonia are called ammonolysis or ammonolytic reactions. These are analogous to hydrolysis reactions and involve the attachment of ammonium ion or amide ion to the reactant. For example, hydrolysis of SiCl4. Similarly, ammonolysis of SiCl4. It may be noted that in ammonolysis, an atom or ion from a substance is replaced by a nitrogen containing ion or radical. Now these are some ammonolysis reactions of sulfuryl chloride to give sulfamide and other reactions. Yeah, these are the reactions of ammonolysis. Okay, so now fourth reaction of liquid ammonia is complex formation reaction. Many complex formation reactions in liquid ammonia are reported which are similar to reactions occurring in the aqueous system. For example, zinc nitrate react with potassium amide to form insoluble zinc amide which dissolve in excess of amide due to formation of complex compound of zinc. These are the reactions. This reaction is analogous to reaction of zinc nitrate with sodium hydroxide in water. These are some other complex reaction in liquid ammonia. Now, fifth reaction of liquid ammonia is formation of ammoniates. Just as water form hydrates, Ammonia also form ammoniates with many inorganic salt. In this compound, the ammonia molecule are coordinated to the cation. Some typical ammoniates are given below. Sixth reaction of liquid ammonia is redox reaction. Liquid ammonia act as an excellent medium for redox reaction in reaction. In liquid ammonia, the oxidizing action of strong oxidizing agent is weaker than in water solution. For example, HNO3 in liquid ammonia does not act as an oxidizing agent. Similarly, KMNO4 in liquid ammonia act as a very weak oxidizing agent. On the other hand, the reducing agent show increased reactivity. For example, alkali metal act as very powerful reducing agent in liquid ammonia. For example, sodium metal in liquid ammonia reduces CuI to Cu, KMNO4 to K2MNO4, etc. Seventh reaction of liquid ammonia is solutions in liquid ammonia. The dielectric constant of liquid ammonia is low. Therefore, it is expected to be a poor solvent for ionic substances. Among the inorganic compound, all ammonium salt, nitrate, thiocyanate and iodides are soluble in liquid ammonia. Oxides, hydroxides, carbonates, phosphate, sulfate and most of the sulfides are insoluble. Most fluorides are insoluble in liquid ammonia and the solubility among halides increases as fluoride, chloride, bromide and iodide. Most of the iodides are soluble. Calcium and zinc chlorides, which are extremely soluble in water, are quite insoluble in ammonia. Organic compounds such as halogen compounds, alcohol, ketones, ester, simple ethers, phenol, amines, nitro compounds, etc. are readily soluble in liquid ammonia. Aromatic hydrocarbons are sparingly soluble. Paraffins and benzenes are non-soluble. Among the elements, metal like magnesium, aluminium, zinc, calcium, lithium, selenium, manganese, etc. are only slightly soluble in liquid ammonia. Alkali metal and alkaline earth metal are highly soluble in liquid ammonia. These form very interesting solutions and are discussed below. Non-metals like sulfur, phosphorus, iodide, cesium are soluble in liquid ammonia. Next topic is solution of alkali metals in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metals. The important characteristics of alkali metal solutions are: first, these are blue in color and the color is independent of the metal dissolved. Second, when the concentration of the metal is increased, the color changes to bronze and show metallic appearance. Third, these solutions are conducting and show strong reducing properties. Fourth, these solutions are paramagnetic and the paramagnetic character decreases with increasing concentration. Fifth, if the reagents are pure and dry, sodium solution in liquid ammonia are stable and can be preserved for several days. When alkali metal are dissolved in liquid ammonia, they ionize to give metal ions and valence electrons. Both the alkali metal ion and electron become solvated by ammonia molecules. The ammoniated electrons are responsible for blue color of the solution. This is due to the absorption of visible light by ammoniated electrons. The electrical conductance is also due to the ammoniated cation and ammoniated electrons. The conductivity of a metal in liquid ammonia is comparable to that of an aqueous solution of a typical ionic compound. As the concentration of metal increases, the blue color changes to bronze and finally the blue color disappears altogether. This is due to the fact that impurities such as iron oxide catalyze and conversion of metal into amide. On evaporating the alkali metal ammonia solution, alkali metal can be recovered. Next is advantages of liquid ammonia as a solvent. First, the dissolution of alkali metal without chemical reaction is one of the greatest advantage of using liquid ammonia as a solvent. Second, The alkali metal solution are strong reducing agent, even stronger than hydrogen. Third, ammonium salt dissolve in liquid ammonia, act as amino acid, and these find applications in preparative chemistry. They can also be used to prepare silane, arsine, etc. Fourth, the tendency for solvolysis is less in liquid ammonia than in water. Some disadvantages of liquid ammonia as a solvent. First, the liquid range for liquid ammonia is from minus 33.3 degrees Celsius to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with liquid ammonia. Second, liquid ammonia has an offensive odor, therefore it requires special technique to use it as a solvent and as a reaction medium. Third, liquid ammonia is hygroscopic in nature. Now next non-aqueous solvent is liquid sulfur dioxide. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvent because it does not contain any hydrogen atom. Under normal conditions of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and is easily maintained in the liquid phase. It has a wide liquid range from minus 10 degrees Celsius to minus 75.5 degrees Celsius and can be used as a solvent. The characteristics physical property of liquid sulfur dioxide are given in this table. Physical properties like freezing point, boiling point, density, viscosity, dielectric constant, dipole moment, and specific conductance, etc. Now here is the structure of sulfur dioxide molecule. This is the structure of sulfur dioxide molecule, and this is a resonance hybrid of the resonating structure. Next is solubility of compound in liquid sulfur dioxide. Among the inorganic compound, iodide and thiocyanate are most soluble. In case of alkali metal halides, the solubility are in order Mi, Mbr, Mcl, Mf. The uninegative polyatomic anions such as ClO4 negative, NO3 negative, BF4 negative, etc. are generally more soluble in liquid SO2. Salt of multinegative anions such as SO42 negative, SO32 negative, S2 negative, O2 negative, etc. are practically insoluble. Among the organic compound, aromatic hydrocarbon and alkenes, pi-bonded compounds have a very high solubility in liquid SO2 in comparison to saturated hydrocarbons, alkanes. Pyridine, quinoline, ethers, halogen derivatives, and acid chloride also dissolve in liquid SO2. Next is autoionization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to autoionize as 2SO2 gives SO2 positive and SO32 negative. The thionyl ion SO2 positive is analogous to the hydronium ion H3O positive, and ammonium ion NH4 positive and sulfite ion SO32 negative correspond to hydroxyl OH negative and amide NH2 negative ion of the aqueous and ammonia system respectively. Now we will study reactions of liquid sulfur dioxide. First is acid-base reaction. Liquid SO2 undergo autoionization. According to solvent system concept of acid and base, the compound which give thionyl ions in solution of SO2 would behave as acid, whereas compound giving sulfite ions in liquid SO2 would behave as base. And this is the reaction. Next is solvolytic reactions. Solvolytic reactions in liquid sulfur dioxide are not as common as they are in other protonic solvents such as ammonia. Some reactions are given below. First is ammonium acetate is solvolized in liquid SO2. This reaction is analogous to the reaction of ammonium acetate in water. Second is certain covalent halides such as PCl5, PBr5, UCl6, ASCl5, WCl6 undergo solvolysis in liquid SO2 in sealed tubes. These are the reactions given. Many binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, etc. do not undergo solvolysis in liquid sulfur dioxide. Third reaction of liquid SO2 is precipitation reaction. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to selective solubilities of compounds. The precipitation of several insoluble compounds in liquid sulfur dioxide can be carried out by treating them with soluble compound in sulfur dioxide. Some of these reactions are given here. Fourth is complex formation reaction. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, the solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium iodide. This is due to the formation of the complex Ki3 or RbI3. Similarly, the increase in the solubility of cadmium iodide and mercuric iodide in liquid sulfur dioxide is attributed to the formation of complexes. Now again, these are some reactions given. Fifth reaction of liquid SO2 is organic reactions. A large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and it is a relatively inert solvent. Some common examples are: first, sulfonation of aromatic hydrocarbon by sulfur trioxide or chlorosulfuric acid. Second, liquid SO2 has also been used as a solvent for Friedel-Crafts type reactions. Third, it is also used as a solvent for the addition and substitution of bromine reactions. Now, sixth reactions of liquid SO2 is sulfur dioxide of crystallization. These reactions are also called solvation reactions. Like water and ammonia, salt having sulfur dioxide of crystallization have also been observed. Some examples are NaI.4SO2, Ki.4SO2, Lii.2SO2, Bai2.4SO2, AlCl3.SO2, KCNS.SO2, etc. These are formed with the highly soluble salt and are analogous to hydrates. Now, the last reaction of liquid SO2 is redox reaction. Though gaseous sulfur dioxide behave both as oxidizing and as reducing agent, liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply acts as a medium for certain redox reactions. For example, iodine is liberated from Ki in the presence of SbCl5 in liquid sulfur dioxide. Some special features of liquid SO2 as a solvent. First, it has low boiling point and this allows its easy evaporation and therefore removal from the reaction mixture. Second, it has low melting point and therefore it allows reaction to be carried out at low temperature. Third, liquid SO2 is an inert solvent. Fourth, it has unusual solvating power for both covalent and electrocovalent compound. Fifth, it is a better medium for covalent compound like hydrocarbon and is used for the purification of some petroleum products. Sixth, it is used as a diluent for the superacid medium which help in reducing its viscosity without affecting its acidity. So, here's the end of this chapter come. Thank you.